So I will invite Professor Davaleswar Panda to give the next keynote, please. And you already have the slides. So, oh, yes, cool. So then I will acknowledge also that DK, we know for 10 years now. We met in South Africa. Why not? So, and over the years, well, we have been in a friendship, and he kindly came on the past Multicore World. This time he's only for today. So it is not that commitment or US government policies or what. Please.
Okay. Thanks, Nicholas. Good morning. Good jet lags and all. Good afternoon. I just arrived. My class got cancelled. I just arrived today morning. We attended here. Oh. Hello? Yeah. Okay. So that's what Nicholas was telling. I work a lot of logistics. I have to be in DC local time Tuesday night. There is an NSF event taking place on Wednesday morning, so I have to speak there. So that's how we coordinated. So anyway, thanks again for the invitation. And this is my second time here. Last time, I think I met many of you. If you remember last time, I was talking about this new NSF-AI Institute, ICICLE, which I'm leading. And based on the interaction with Nicholas and others, today I'll be going into a little bit more details of one of those projects which is focusing on digital agriculture. There's a lot of interest here in the New Zealand APAC region about digital agriculture. That's what I'll be talking here today. I'll be giving, as Nicholas indicated, I'll give a very brief self-introduction, followed by some of the overviews, if you're not familiar, of AI enabled. I think there's something. To the NSF-AI ICICLE Institute, and then how we are enabling through this AI Institute, having some solutions. I'll go into some detailed challenges and solutions. And not only we are working as researchers, but we are also producing a lot of software. And that's what I'll be talking about, and a lot of people have started using it. So those will be the software releases, users, collaboration, and then conclude. So just to give a brief self-introduction, many of you know, I know many of you here. I mean, I have been working in this HPC field for almost like 33 plus years. I'm becoming a very, very old person now. Many of you might be knowing this MHAPI's MPI library. We started that in year 2000 when InfiniBand, as you know, was the first introduced in October 2000. Prior to that, I was working in Miricom, Mirinet, Quadrix. Those of you remember those old networking technologies. When InfiniBand came, we were the very first group in the world to have a high-performance MPI. And I'm very proud of my team. We are continuing that for 25 years from academia. That project is sustained over the years. And then now, of course, it supports all HPC interconnects. We also have this OSU micro benchmarks. Now, this is being used by more than 3,400 organizations in 92 countries. Dan indicated to that today in his talk. And just from our website, we have crossed like a 1.86 million downloads just from our project site. Okay, of course, it's a part of all other stacks, Red Hat, Stack, OpenHPC, SUSE, and others. And of course, it has been enabling many top 500 clusters over the last 24 years. So now recently, over the last 10 years, what we're trying to do, because MPI, as you know, provides a very good scale up and scale out. Anytime a new networking technology comes, or CPU, GPU, any of these technologies comes, MPI is the first one to jump in to have a very good, like a scale up and scale out. So now we are trying to leverage to actually do AI on top of that. So we have there is a project here, MPI-driven distributed training and inference, even the big data, Spark, Dask, everything we have brought to MPI level. So that means if you deploy a map stack, you should be able to have like a support for HPC, AI, big data, everything together. So that is the kind of the direction which is going. But what I'll be talking today is that I lead this NSF-AI Institute called ICICLE, and that is focusing on intelligent cyber infrastructure for computing continuum to democratize AI. Okay, I'll go into more details. And especially we have, while developing this cyber infrastructure, we are also trying to validate it. So there are like 3 use-inspired science cases there. I'll be going into more details on one of these, the digital agriculture, but we also have animal ecology and smart food security. And especially ICICLE, I'd just like to indicate Professor Tefik, he's there. He was actually the program manager at NSF. He gave this award, okay? So he can see how much progress we have made. And of course, Dan also sits on our executive advisory committee. He knows many of these slides. And of course, there are many of you here who have actually served as yearly reviewers. NSF has the yearly review program. I see many of you there, and they have also given us good feedback. So we are on the 4th year of that institute, and we are continuously going very strong. So I'd just like to acknowledge your help. So this is a very big team. I think 100 plus people. We just had like 3 weeks back, we had this all hands meeting in San Diego. So this just shows a photo. But more importantly, what I'm trying to present in this talk is the actual contribution of this digital agriculture sub-team. Okay, so they have done all the work. I have not done all the work, but I'll be presenting all the results from there. And as you can see, like they are from all different institutions. So if you take a look at digital agriculture, I mean, take a look at like where world population is steadily growing. This is some statistics. In 2050, there will be 9.8 billion people, okay, in the world. And of course, as many of you know, the climate is changing. And what people are predicting compared to 1985, if you go to 2050, almost 50% of the land will not be arable. They will be totally destroyed, okay, or changed so that you cannot actually produce anything. So that means there is a very big pressure on, you have to gain some wide gains in the crop management, okay, so that the limited land we have, and from those land, we have to harvest in a much more higher yield or economically solution. So this is where I think this motivation comes. And especially traditionally, as you know, the agriculture has been just built on the farmers, their historical knowledge. But every time technology changes, you know, the technology comes, just like our industrial revolutions almost 200, 300 years back. So same thing is happening to the agriculture field. And as technology advances, the next generation of agriculture professionals, I'm not saying farmers, but these will be agriculture professionals, they will actually include engineers, computer scientists, data scientists. So they will work together to solve these problems. And that's what we are seeing for the last several years. And one of the ICICLE Institute's objective is to really accelerate that to the next level. And at the same time, we also want to democratize. That means currently also there are some solutions, like AI-based solution. I mean, so let's say you go to John Deere, they will say, oh, I have some solution. But then you ask for the price, $400,000 million, so you have to give them to get that solution, and that's also very limited. So that is not getting very widely popular. Of course, there are rich farmers, they can afford it, but the poor farmers, poor countries, they cannot afford. So this is also one of our objectives, to really democratize, make the solution very general purpose, make it available, so that not only the end users, but a lot of companies, other people can take our software and build on top of that. So that is our goal of this NSF-AI Institute. And in that way, big and small farms can use it, even staple or specialty crops can use. It can also be used by underrepresented communities. And of course, there are a lot of big issues about privacy, ethical consideration, sovereignty of data. I think we have a panel just after this. So that also we need to take into account to see how the solutions can actually try to handle this. So let's take a very interesting look. And as I'm working in this field, just to be very honest, I mean, 5 years back, I had zero knowledge on agriculture. Okay. But while working in our team, actually, not only computer scientists, we have actually faculty from Department of Agriculture. So these are the people who work with the end farmers. So continuously every day I'm learning, saying how that field is working. So this is a very nice picture which says, like, this is a production agriculture. So you have to go through multiple steps, like a pre-season planning, like slope, elevation, drainage, field preparation you have to know. You have to do planting. You have to do in-season application, harvest, post-harvest. And a lot of these things are dependent on a lot of other factors like soil nutrient moisture, residue cover on soil surface, non-uniform emergence, nitrogen deficiency, defoliation. And if I want to use AI in each of these steps, gradually I'll show you, you need to collect a lot of data. And as you know, the AI is dependent on data. If you don't have data, you cannot build your models. If the model is not there, you cannot do inferencing. So it starts with always the data, and this is where we are working with a lot of like our faculty colleagues and who actually work with the end farmers to get all those data. And at the same time, there is also advances taking place on instruments. And these are just like a medical field. If you go here, there are a lot of these instruments continuously coming, like starting from drone to gas analyzers to soil moisture temperature analysis. And at the same time, as people are working on, a lot of data is also being available. Okay, like weather data, soil data, farm management data, satellite data, and all these. So there are three things are happening here. So there is a lot of instruments are coming, availability of the data, and then there is this production cycle to see how to incorporate all these things together. So that is the big problem what we are trying to solve here. Can advances in HPC, AI, and big data help in the digital agriculture, and if so, how? That's what we want to answer here. So let me take a quick look back at the HPC field, which many of you know. I mean, go back like almost 50 years back, scientific computing and HPC started. Then HPC big data analytics came in another 25 years. And of course, the AI started like in 2010. But then these were like the traditional thing, I'll say, where you get the data, put it in your supercomputer center, and then you operate on those and put the results back. But now if you take a look, I think we heard that from some of the talk, Kate also indicated this computing continuum, okay? So this is what is happening. Instead of the left-hand side, we have this right-hand side. So the data is not static these days. It's not like you just collect the data, put it somewhere, and then operate on it. Data is continuously coming, okay? So this could be coming from like the drones, could be sensors like on the field. Continuously we are getting like data on the soil, whatever the quality, the moisture level, and all those things. So you need to take this data and then trying to see what to do where, like you might have like a edge, near edge device, cloud, all those things, and you need to see where to run what computation. How do I bring the AI? Which part of the AI will run where? So that the entire software infrastructure we need to design. So let's take an example, and which will go into a little bit more details. This is a motivational example. Like if you have a big farm, let's say very simple things like can I detect like what has happened, what kind of diseases are there in the field. I'm sure like in all our gardens, when you put some rose and all, or any other vegetables you might have put, like you started getting some different kinds of diseases coming. And then of course we take a look at the book and see, oh, this is what I'll be spraying. But this we just do blindly. But think of acres of field. Can I use AI with help of a drone to really go and then very quickly see which part of the field has what kind of disease? And if I can have that through AI, and I'll show you how, then you can actually take that information and give it to the farmer so that the farmer knows exactly in this part of the field I need to spray pesticide 1 or pesticide 2. Or in fact, there are now advances taking place. I can feed that into an intelligent tractor. The tractors are actually having video cameras. In fact, many advanced tractors even have GPUs, NVIDIA GPUs and all. So in real time, they can take this data and then precisely go and do precision spraying. And if we can do that, not only we can reduce the cost, but it has the biggest advantage is the environmental impact. So that we are not unnecessarily like putting pesticides all over the farm. And in that way, like we can hope to do yields will be better. We are helping the environment and reducing the cost. So let's see how to achieve that. So within that, if you go, there are a lot of issues again. These are the domain challenges. Like once you have some crop, what happens to the residue cover on the soil surface, because that will affect the next crop, whatever you are trying to do. Same thing is soil aggregation size, like how much compact, or what the materials is there. It depends on the rain, it depends on the kind of various environment factor. There is also like how the fields is like emerging. You see, there could be a non-uniform emergence. That means once you have put these seeds, if you see that like some parts are not growing steadily over a period of time, that means there is a problem. Okay. In fact, that means the yield will be getting affected later on. Similarly, like you might have some nitrogen deficiency. If you can detect that, you see like some of the leaves become like yellow kind of thing. So that means having nitrogen deficiency. If you can learn that quickly, then you spray some more or put some more nitrogen. Similarly, like these are different like worms, European corn borer, corn leaf aphid, beetle defoliation. So all these things happen, and how to use AI, okay, and HPC, everything come together. So these are a lot of these challenges. I'll not go into details. Like a very high level, you can see this is like an AI problem. How do we get like a data collection and cleaning? So that's the first thing. If we have the data, how do we do model training? And then if we have the model, then can I, that drone example I indicated, can I actually put the model, a copy of the model in the drone? If the drone allows me have enough memory and computing power, it can actually do real-time inferencing. And if not, drone can only take the image and then send it to a cloud or send it to your edge, then the computation will happen there to get this. And then think of so many different crops and so many different kinds of diseases. Okay, so you need to have models and data for all these variations. Otherwise, you cannot get the correct thing. And this is field, agriculture is very similar to also medicine field. Same things is happening in medicine. Like just like our human beings, there are so many diseases, and people are trying to bring AI there. And they're also the same thing, like how quickly we can use the AI. So here there is a need for like the models common. Okay, so that a lot of these models like Hugging Face and all, similar kind of things, the model has to be developed for agricultural field so that when I'm trying to start a drone mission, it exactly knows like what model to pick based on the region, based on the crop, based on the diseases, so that it can work on it. And what we want to do, I'll go into a little bit more into detail. This is one of the high-level objectives also of ICICLE, to do plug and play, because we want to generalize the solution. We are not like a John Deere, which will say, okay, just use it for soybean in Midwestern Ohio. Okay, rather we want to make it democratized so that different people can actually use that and select the appropriate model in a plug and play manner. And then, of course, to achieve that, we need to have a comprehensive end-to-end AI/ML workflow, okay, and overall architecture. And then, with all these things, we also want to make it much more easier to use. Okay, I cannot tell all these, an agronomist or farmer saying, okay, I have a good solution, but you need to learn TensorFlow or PyTorch. They will say, okay, bye-bye. Okay, so we want to convert that into a conversational AI interface, and in the end, we want to provide it as a service. So just think of a service on your iPhone for a $9.99, just like you subscribe to Netflix or any of those other things. So we want to convert everything, whatever the cyber infrastructure we are trying to do, package them through a conversational AI, and then this farmer can wake up in the morning saying, okay, can I get an idea of what has happened to my field? Okay, or that is only like a crop management, but let's say the farmer decides to harvest. There are a lot of decisions happen in the harvest. Should I harvest today because rain is coming tomorrow? What is the market price? So all these things can also be done together in this our infrastructure. So through conversational AI, the farmer is asking, okay, should I harvest today or wait until tomorrow? So you'll get an answer. So we are having a focus on also the conversational AI, the foundational models, all those things we are trying to bring, and also the privacy preserving techniques. Because many areas, what happens is like you might be in the same region. If I want to develop a model, I need data from 100 farmers, but might be everybody's not ready to share the data because they want like their own data, they want to make it private. So how do I build these models through federated learning, those kind of techniques, so that they get the benefit, but without like sharing all the details. So these are the kind of challenges. So what we have done, I talked about this computing continuum. So if you see here, this is like our ICICLE logo. So as you can see, it is deliberate, like there's a smaller version. You can think of a lightweight ICICLE here, lighter. This is a little bit medium, or this is a dense. So we're trying to develop this distributed framework of that ICICLE software structure, which will run where, but they will be running together. And to solve all these kind of problems here, like I'll just quickly show, it just shows self-driving farms, how do you do data generation, novel model architectures, data sets, public hack services, adaptive AI as the edge. So a lot of these things need to get mapped to different parts and to make this solution very generic. So with that kind of a background, let me go into a little bit of the NSF-AI Institute. So over the last several years, if some of you are not familiar, National Science Foundation in US has given awards to 27 of such AI institutes. And each one is like a $20 million over 5 years. But each one has a specific focus. Okay? And they encourage all these institutes to work together. I'll come to that later on. So our focus, ICICLE, has been funded by Office of Advanced Cyber Infrastructure. This is where Tefri was as a program manager. So our objective is, in fact, our institute is a little bit harder compared to others because other people are just publishing and showing that, yeah, I have 200 papers. But our institute is not only to do research, but there is a mandate that it has to be converted into software. Okay? So we are working very hard to really have this kind of software based on the heavy R&D we do, so that the end users are actually getting a solution out. Okay, so that is why we are very unique here. And ICICLE is the only one focusing on the intelligent cyber infrastructure. This is the, if you can just do a search, ICICLE.ai, or go through this QR code, you will find it more details. So the broadly it looks like this. Here we have the computing continuum. I'll mostly talk about digital agriculture, but we also have two other focus, smart food distribution security and then animal ecology. And just to validate these things, okay? And at the same time, also we take inputs from these, and we are also gradually, we are currently in the year 4. So we are also trying to develop a common framework so that these can be used, several of these components, like can be used for this all together, so that we are not duplicating the effort for each of these areas. And later on, I'll conclude that this framework actually can also be useful for smart medicine, smart transportation, because a lot of these components are very generic, okay, and you can use it for other areas. And this is where in the middle we have the ICICLE infrastructure seats. And this is a very large organization. Here you will see like a coast to coast. I'll not go into more details. This is the US map. And we have around like 13 organizations. There are 24 faculty. We have a lot of staffs also, okay, because we are really developing the softwares. And of course, we have around like 50 to 60 students, and there are many collaborators who are working together. So Oishu is the overall lead, and I am the overall PI, but every day is like this one is consuming most of my time these days compared to my other projects, what I indicated earlier, around 110, 120 people working here. We have also gone global. Like once we started working, in fact, there's a joint project between US and India on the same. I mean, agriculture problems are there in every countries, but you cannot take a solution from one area to the other area. Okay, like let's say in US, in Ohio, we are focusing on soybean or corn, whereas in India, they want to focus on potatoes and onions. Okay, so question is, how do we generalize and how do we also convert some of the solutions into different domain-specific one? So, and very similar issues also come across these. And so here the goal is to build upon the existing ICICLE infrastructure, both the cyber infrastructure and AI capabilities. And we want to leverage contextual conditions in India for digital agriculture that differ from the United States. So gradually we are working with the PIH Mumbai and then gradually seeing what are the similarities, what are the differences. Okay, once you understand that, then we can try to generalize into other countries, other crops. So this is how like a very high level overall vision looks like. This is our the ICICLE thing. This is the true conversational AI, and this is where we want like somebody farmer or agronomist to just to get all the information through conversational AI. And within that, this is where like we have foundation systems AI, we have CI for AI, AI for CI, software architecture, privacy, accountability, data integrity, visual analytics, and of course, all these things need to design with a co-design. Okay, because not everybody has all the knowledge, and that's what we are working on. This is a very dense slide. I don't want you to spend time, but for this across the high-level thrust, what I indicated, within thrust, let's say foundational system AI, we have issues like how do you create these knowledge graphs? How do you create model commons? How do you do adaptive AI, federated learning, conversational AI? Then this is like a CI for AI, like high-performance training, data management, edge intelligence, adaptive edge wireless, control coordination. And we also have a very nice focus on AI for CI. Not CI for AI, you can think of AI for CI. As we are developing the cyber infrastructure, can we learn from there? okay? And then use those techniques to have better cyber infrastructure. And of course, there is a privacy, accountability, and integrity. So let me go into a little bit more details, okay? That is a high-level overview, but I'll go into now much more deeper into the this agriculture. So if you think of, just let's take a look like a crop health diagnosis. So I indicated some of these things like the factors: residue cover on soil interface, aggregate size, crop development, non-info emergence, nitrogen deficiency, etc. And look at this. This is where I can try to find out like a 5% nitrogen deficiency is happening, or 10%, 20%. So we need to take a lot of this data and then come up with a cyber infrastructure solution, and where we can do actually the management. Okay, so we are taking the data, building the models, taking the inference, but in the end, we want to actually give this feedback to the real farmers or to the tractors, whoever is operating there, so that the entire solution can be used. And then if you go down, this is again a very dense chart, but there are so many factors I indicated here, like a sunlight, air, temperature, water, genetics, all these things have an impact. So everywhere we need to see how to use that AI in a very systematic manner, so that we can have this like a different kinds of phenotypes, like timing of in-season treatments. How do I estimate yield? How do I actually estimate like the soil moisture? Should I put more water in our field, or see the weather? If the rain is coming, then I don't have to do this. So all those decisions you need to take in a very dynamic manner. And this picture actually shows a very nice life cycle. Okay, so think of like a farmer who was just have a corn field, and multiple things happen. Like let's say in the beginning, you need to see you put the seeds. Might be the seeds are not growing. You need to in the first few weeks, you need to take a decision: should I reseed? Okay, because might be something has happened, and then the next, as I go into, then might be some fertilizers should I be putting. So these are like the different stages, and then gradually as the crop becomes larger and larger, then you need to see, okay, weeds have come. So how do I actually take care of those weeds in the field? Because otherwise they will cover the entire field. And then as I go, then there are all these different diseases can happen. So I need to have plant disease management. And then in the end, this is what is also important. As the things are coming, I never knew this, but these crops, just like oils and all, they lock the prices 6 months in advance, 9 months in advance. Like whatever they harvest, how much they will be selling. So you need to have all this understanding that how my field will be giving you the yield, so that you can actually properly lock the prices. Okay, otherwise you will be losing, or hopefully you will be winning. But if you don't do proper things, then you might be losing here. So the end goal is to really, these farmers, like starting from this agronomy, if you take a look at this farming, you talk to some of the farmers, it's a very stressful activity actually. Okay, many times I feel like after talking to some of them, I'm in a better life. I'm doing computer science, funding may be going away, but there are a lot of other factors, but they're actually dealing with it on a day-to-day basis. Okay, and what our goal is to really take advantage of all this latest equipment, technologies, and the end goal is like they really become profitable. Okay, as a profession. So that's what we want to achieve, to provide AI-based decision support, to enable these all agriculturists to make more informed agronomic decisions on treating their fields using their equipment and technology, so that they can actually improve profitability in a sustainable manner. Okay, that's what is the very big goals we are trying to put it here. So in order to do that, so this is the kind of the entire cyber infrastructure we are developing. I'll go into a little bit more details on the components to understand crop health issues, and of course, for all these AI, as you know, I mean, we need to have HPC, we need to have big data. So those we know very well, okay, over the years. So the question is, how do we customize for these environments? And then in the end, we want to actually provide them into the crop management interventions. And in order to achieve that, now the example I gave, like a drone is flying, getting the data. Similarly, sensors are getting data from the fields. All those things we need to take in this computing continuum, and then build the AI models, not only the training, fine-tuning, and also in the inferencing. Where do you do computing? How do you move the data? Where do you do the control, so that everything has to work in a very seamless manner? And not only that, we can actually do it in a plug-and-play manner. as I indicated earlier. Also, the objective is like how do we do in a configurable manner. Okay. So I'll just talk about these 5 components. I'll go into each one of these, like how we have developed this end-to-end modular workflow with plug and play capabilities. How do we do efficient data collection, model building? We have actually, there is a group which is working also on aerial crop scouting, called the Open Pass. Then there's a lot of data transfer you need to take care to HPC to edge to the big centers. It might be even from the drone to the HPC. So we have a project there called RMR. And then we have integrated everything as like an AI-based service. Okay, and I have a small video which I'll be showing towards that. So if you take a look at this, so we studied quite a lot in all these details, and this is where we have actually all these blue boxes, our ICICLE boxes. Okay, so we have like a big component in data pre-processing, how do you do semi-supervised labeling, and then this is where the very agriculture-inspired model training, then we have the trend classifiers, then we're also taking some of these geospatial processing data, and then working together this entire pipeline from the left-hand side to the right-hand side. So in order to do this, I think Nicholas had seen this picture. Some of you might have seen this picture. We have developed this into like a 17 different components. Okay, in the beginning it may look very complicated, but that is our idea, that it's at a high level you can think of like there's a lot of this data collection and pre-processing. So each one of these is a module, and this module need not be static. It's actually, that is where we are trying to say this is configurable. Okay, so that means if somebody has like a data transfer from drone to edge, we can have 4 solutions there, 5 solutions there. Adapt them based on the field, based on the situation, based on the cost. Okay, so people can actually do this plug and play manner. Same thing is the model training, inferencing, and visualization. And the goal is really to make it modular and configurable, and then plug and play. Okay, so that's why we're trying to generate these things. And somebody might be just taking, and we want to make it like inclusive. So if anybody else, like not only we are working on solution, but if somebody else saying, oh, I have a better model, we should be able to take it. Okay, so that we are not restricting. So it is not a very, like if you go to, might be a John Deere, their solution can be mapped here, but that is very hardware to their device, okay, or their infrastructure. Similarly, Microsoft has a solution on the digital agriculture that is also very geared towards Azure. With some of those components you cannot take and modify. So here we are trying to enable the world, okay, so that people can take it, people can modify it. If they would like to contribute back their solutions, we can also take it and then make it available in the next release. So then let's go into the efficient data collection. So these are the data from some of my colleagues who are working in the agriculture department. So if you take a look, what they're saying, like building the data sets. As you know, the AI is always about collecting, transmitting, cleaning, labeling, training data sets. Unless you have clean data, you don't get all those accesses. And what they have found out, that almost 60% of the time, they waste in pre-processing. Okay, all this data you have to understand, label, clean, then only you can build the model. Otherwise, the models will be wrong. And this is where we are actually working on to enhance it. So these are like some of the OSU, as some of you know, like in US, many universities are called land grant universities. So Ohio State University is like a land grant, started like 225 years back. So the state of Ohio faculty actually work with a lot of farms within OSU, within state of Ohio. So we are actually working with a lot of different farms, like for example, Worcester Cinder Farm, Western Agricultural Research Center. So we are taking data not just for one particular crop or a particular season. It's like data is coming for 3 years, 5 years. And then that is the data we want to take. Okay, so that gives us a much more finer granularity of what we want to do. And so then the question is like the georeferencing through US imagery. So a lot of things you can do locally, but these days with satellite data, you can actually correlate. Okay, so you get very big region, and satellite data are also available over the years. So we can actually correlate and make our models much more stronger. Then there is a informed sampling. How you these pictures, many different pictures, if you see, these are the like the agronomists exactly know which is the right, which is the wrong. I don't know. Okay, so we are taking from their help, saying from this image, like the appropriate labeling you need to do, saying which are the correct images, and built on that, we build the models. And then, of course, then they are adapting their ML model architecture. So we have a team who is actually working both from computer science side as well as from the agriculture side, saying how do we make these models much more simpler. Okay, so all those things are happening in the data cleaning. So then the question is, okay, both for like sensors, we can get the data depending on the wireless network and all. But if I want to take really the drones, there is a lot of complications. How do you really take the data from the drones? I never knew this again. Okay, I mean, my simple assumption was that you just fly a drone and you get all the data, but that's not true. Like if you think of just ask a question like, is this healthy soybean field? But of course, first I have to fly the drone, and many times, the drone capacities, it may run only for 15 minutes. You run out of battery. Okay, so you need to come up with a very optimal way how the drone will go. Okay, so this is where it shows we have some very good research. My colleague works here, like how exactly you take a path based on the fields, based on the health of the field, or what we have done, like we have really taken parallel processing to the field. Instead of flying one drone, we can fly 8 drones if you have availability, and they go through different parts. And just like our traditional computational fluid dynamics and all, we have the edges and all those things, you exchange information. You can take the same idea, okay, and coordinate all their flying, and then in the end goal is here. So as you can see here, this picture summarizes, like from a field, in the end, I can come up with this heat map model. Okay, so this heat map model here, it shows only 2 colors, but I can have multiple colors. The red says that there is a disease there. Okay, and it can actually tell you what kind of disease is there in that field. Okay, there could be multiple diseases. So in the end, we want to convert this into a heat map. And this is my colleague who is the expert here, Chris Schwartz. And in the end, this is the information we want to actually push it to, either give it to the farmer through the iPhone app kind of things, or it can be actually given to the tractor itself. If you have an intelligent tractor, you feed it, and the tractor exactly knows from this location that as the tractor is moving in this area, I have the disease 1, I should spray this pesticide. Okay, so that is the kind of the end-to-end solution we are trying to achieve. So then the question is, I'm just introducing this component. So we have some of these components all integrated together. It is working. I'll show that demo, but everything is not yet integrated. We are still in the year 4, but our end goal is to really put them all together in the next year so that we can have the complete solution. So then there is issues. How do you do data transfer between edge to the cloud? So here if you see, like let's say that drone, you take it, you get this drone image. So most of the time what happens is there is like as the drone is getting the things, it may not have enough memory to store, or it not enough like a storage capacity. So it needs to be moved to somewhere, the near edge or to the cloud or HPC. That also depends on the bandwidth, how much you have availability. Is that wireless is strong enough, or you need to come to a base station, and then from the base station you go to the other thing. And many times what has happened, what we saw in the practice, that this entire file has a high redundancy. What actually matters is like you get information on the edges, just like that CFD kind of things, ideas you can take. And then if we can make some optimizations of what data needs to be sent, often with like less than 10% of the image, then I can actually save time. Not only save time, I need less storage space in the cloud and all. So then this is where like one of my colleagues is working here, the chunking these images, storing it as an object, and then some people have done it using the Amazon S3 store chunks or Microsoft Azure Blob, etc. So they have introduced a RMF architecture. And this RMF architecture is now integrated as I'm getting the data, like in the training phase, as I'm getting newer data, I need to start the training also. So there is a integrated pipeline which has been done. So as the data starts coming, chunk by chunk, the training has already started. Okay, so that we are not losing the time. So this is the overall RMF architecture. And through this, so this is actually a real DB paper. It just will be presented in the next few months. And what they have shown that we can actually make this like a 2-dimensional cost to complete workload and the queries per hour, you can make it actually 1.5x faster and 9x cheaper. Okay, so those are the kind of the solution. Also, every component we are trying to optimize performance, scalability, and when we put it all together, then the entire end solution will also be high performance and scalable. So finally, the question is how do we integrate together? So this is where we have actually, there is a solution we have, it stands for, it. There is an acronym which is harvest, but it's not just for harvesting, it's for the agriculture, the entire pipeline. We have multiple components here. There's a very nice dashboard here. You will see there is a data collection, pre-processing, model training, visualization, model inference, everything you can do. This is like our AI service. Okay. So there is a nice video. Let me play here.
Welcome to the future of agriculture. This is ICICLE's AI cyber infrastructure for end-to-end processing of digital agriculture use cases. As a user of this framework, you can easily compose and manage your jobs all from one convenient and user-friendly interface, which is connected to an HPC backend where your jobs will be accelerated on modern GPUs and CPUs in a distributed fashion. Let's get started. The dashboard is your control center. Here you can select from many modules to compose your new jobs. Depending on the nature of your job, you can take advantage of one or a combination of modules, including data collection and pre-processing, image labeling and high-performance model training, model inference, and visualization of results. The dashboard provides a comprehensive overview of your resource usage, data storage, and processing times. Let's walk through an example of creating a job which uses all of these different modules. The use case here is classification of growth stages in a cornfield, where the goal is to train and use a deep learning model to analyze phenotypic data and provide detailed insights on the growth stage. Let's create the new job. The first stage is data collection and pre-processing, where you can import your data from Model Commons or upload it from your edge device directly. Once the pre-processing is done, we will have access to download and examine the pre-processed dataset. For now, let's move on to the next step, which is the model training. This page shows a list of model training options. The values will be populated by default or beginner users. At the same time, advanced users can adjust the training hyperparameters. The domain expert will then provide a number of label images for each class. This current page shows the first growth stage class, as shown in the very top. We can navigate through the samples and select representative images. Then we'll click Submit to move on to the next class to be labeled. Once the images are labeled for all the classes, distributed DNN training will be submitted automatically on behalf of the user. For inference, the user can select the inference task they wish to perform. In here, our task, again, is growth stage classification. Then we can select the model to use for inference. We can hit Submit, and that will take us back to the job overview page. Now, let's go to the final stage, which is visualization. The heat map is a view of the entire field. There are several blocks. Each one of them is color-coded based on its predicted growth stage. The user can click on individual blocks, review the zoomed-in images, and provide feedback to the system if they think the classification is incorrect. Finally, let's look at the results gallery. Here, the user can examine individual images, their predictions, and the confidence score provided by the deep learning model. This job is now considered complete, so let's quickly go back to the dashboard. You can see the updated account statistics with the remaining SUs and storage. The new job list now shows the job that was just completed, and the user always has the option to go back and visit completed jobs. This concludes our overview of the framework. So thank you very much for listening.
So you got an idea, like not only we are having individual components, but we are trying to integrate. So think of like it's very similar to like what happens if we go to a hospital, so like a pathology image is being taken, MRI scan is taking place. So the doctor wants to see everything together. Then very quickly he or she can diagnose. The same thing we are trying to do for the agriculture field so that individual research is happening, but we are trying to integrate and make it very available. And currently, there are 2 copies of these running, and the Ohio Supercomputer Center and San Diego Supercomputer Center. We are working on a cloud development. So the goal is here to bring your own data. We are not claiming, we are not asking, okay, give us the data, we'll do the training for you. Rather, the end user, just like through this dashboard, can actually work. And then we are also providing so that this bring your own data, so that the data and model remains private to the users. So even the model, they can use our service and keep the model. And if they're interested in contributing back, we can also take them and make it available to the others. Okay. So this is where like we are trying to solve these privacy preserving issues a little bit, sovereignty of the data, all those things. So with all these things, very quickly, I'll try to show this overall ICICLE as we are building it, all these different components we have started, making them available. And every 3 months, there is a dedicated software release team who is working all these components, and every 3 months we make this release. So you can actually go to this website, our ICICLE software, and here I am just highlighting digital agriculture component, how we have released, so that as they are now, you can actually download that harvest, whatever I showed you, you can actually start using it. And already we have around 45 organizations from 7 countries are our early users. Anybody can actually come. They have started using many of these components together. At the PER conference last year, we had our first ICICLE user group meeting. We had a BOF. This year also, we'll have our second BOF there. And anybody can actually join this. We have a ICICLE discuss group. So as the users are there, if they see any issues, they can actually report that. And just like any other open source project, we can give feedback. You can also join our ICICLE announce list. And then I indicated earlier, these NSF-AI institutes, our focus is on cyber infrastructure. But now we are started working together with some of the other AI institutes like AI for Opt, AGED, IRA, AI Farms. There are also joint work taking place with some image genomics, NSF Science Gateways, Iowa State universities, and also international also. We have got some interesting going on. I indicated about TH Mumbai, but University of Cambridge. There's a company, TCS in India, is very much interested. IIT Bhubaneswar, there's an Australian National Universities. Also, there's a CNH Industrial from Brazil. And of course, we are looking forward to the collaboration from New Zealand or other places. So let me just conclude here. So through this project, what we're trying to show that the latest advances in HPC and AI and big data can actually enable AI-driven digital agriculture. And ICICLE has been developing the necessary CI components. And the focus is to make it really a configurable, adaptable, and plug and play. Okay. And then with that kind of things, we feel that gradually this field will rise. And then just like any other software stack, we have a community, so that through community input, we'll be able to make it more and more stronger. So the idea, what we described, I indicated earlier, the same framework, you can also think of for other applications, like the animal ecology, smart food, that is our inspired science cases, but you can also use it for smart cities, smart manufacturing, because everywhere that pipeline exists, okay? And we hope that solution will be valid, and this is where we want to move into the future, making this solution not just restricted to smart food or digital agriculture, animal ecology, but go into all other things. So with this, let me close here, and I'll be happy to take any questions now or later, or if you want to have the panel, I'll be there also on the panel. Thank you. Thank you very much.